My name is Debasis Mitra. I actually don't work in this building. I work at Columbia. I'm in the engineering school right over there. And this is joint work with a colleague at Urbana-Champaign and a student who is now with Google. It's about emerging ISP content provider relationships. So I think we might all have noticed that the dispute between Netflix and ISPs such as Comcast were quite acrimonious quite recently, but that it's changed in tone substantially, quite rapidly, really. So, you know, this change was exemplified by Netflix Comcast, and it suits my purposes to highlight Netflix. But I think what's worth noting right at the outset is that what I'm talking about is this movement of content providers becoming their own CDNs. And Netflix is certainly exemplary of that. But others are following. Comcast is actually becoming a big CDN, and as is Facebook. But as I said, I'll use Netflix as exemplary. The key enabler, in our opinion, in this change has been the Open Connect caching system. And what is that? It's a large-scale content storage system located close to or co-located at the ISP's data centers. Now, caching has been around for a long time. Akamai's whole business model is built around that, right? But Akamai is not a content provider. So just to briefly review caching, if user's content happens to be in the cache, then the user's quality of experience benefits because this is not rocket science. This content does not have to traverse the long distances over the internet from the cloud where the content largely resides. It only traverses the last mile over the ISP's infrastructure, and the user's quality of experience is enhanced compared to to the event that the content is not in the cache. And the other factor is cost reduction. The ISP has a vastly reduced cost associated with connecting to the internet. There's less. It's a win-win situation for both parties, which is a very interesting feature of this. If there's a loser, it's of course the transit ISP. So what is Open Connect? Let's just spend a minute on that. It's a combination of hardware and software. The basic hardware unit is a data storage. It's just a box. It's this big. It's 100 to 200 terabytes. This box holds that much data, which amounts to something like 50,000 hours of video, and it costs somewhere between $10,000 to $20,000. The storage, the cache, of course, stores most popular content. The cache updates, which are not trivial, you know, because it's a fraction of the cache content, but it's because the cache content is so large, it's not trivial. But it happens at off-peak hours, like midnight and so forth. The Open Connect appliances, known as OCAs, are embedded in the Access ISP's data center. But it doesn't have to be that. It can also be at the Internet Exchange Point. The idea is that it should be very close to the customer. So a quick, I don't have that much, so I'll be quick about this background. So what are the factors that determine quality of experience in video streaming? There are these 4 things that are well known. It really comes from a paper published in the Communications of the ACM in 2013. Join time, this is the initial time for the video player to fill up. The buffering ratio, the fraction of total session time spent in filling playback buffer. The rate of buffering events. A buffering event is when the video player runs out of content or starts overflowing. That's an event. And the average bit rate, right? These things are. And actually, the little picture shows how, if the horizontal axis time, the first period is just joining, then playing, and then the buffer becomes empty, so you have to wait for the buffer to fill up, and then you start playing. That's the picture shown there. Now, effective bandwidth is a concept very well studied and developed in networking theory, and I just want to mention it very quickly because it plays an important part in our bookkeeping that you'll see in a moment. It encapsulates factors that determine quality of service like delay, loss, jitter, and so forth. It's a very effective bookkeeping method. So finally, what makes large-scale caching effective? To summarize, it benefits all the factors, the 4 factors mentioned above that determine quality of experience in video streaming. It has a cost reduction benefit, which we've mentioned earlier. And Netflix, until very recently, used 3 CDNs, Akamai, Limelight, and Level 3. And now it's its own CDN. So I'm an academic, right? So I call academics that we build models and then we analyze it. So unfortunately, you have to listen to this model and some of the results that come out of it. So it's a bare bones model. What you see on the right-hand side is the content provider's content, which resides typically in the cloud. In the middle, you have the ISP's data center, and adjoining it, as close as possible, is the content provider's cache. And on the left is the user, like you would think. What connects the cloud to the data center is the internet with bandwidth, and here I always mean effective bandwidth of R sub 2. The content size is sigma. The content provider's cache is size S. That's the size of the cache. And finally, the last mile, shown on the left-hand side of the slide, the bandwidth is R1 plus beta. Now, I'll explain what R1 and beta are in a moment. R1 is effectively is the basic last mile bandwidth, whereas beta is an enhancement that the content provider works out with the broad access for ISP. And it may or may not be granted depending on how rigorously net neutrality rules are implemented. So we have 2 scenarios: net neutrality, indicated by double N, where with beta, this boost in bandwidth over the last mile is necessarily 0. And the non-net neutrality case, where beta can be greater than 0, and its value is determined by the contract between the content provider and the access ISP. The key expression here is the user's effective bandwidth, and the expression on the right-hand side has 2 terms, but the key player is this H. H is the cache hit probability, is the likelihood of the content that the user wants to see is in the cache. And that, from network theory, there's a lot going on there, but it's very well approximated by log of the size of the cache divided by log of the size of the total content. Right? So sometimes the cache size will be, the proxy for that will be simply H, the hit probability. And the first term is R1 plus beta times H. In case there's a hit, then all effective bandwidth is essentially the last mile bandwidth. But if there's no hit, then it's the internet's bandwidth. And 1 minus H is the probability of a miss, of a cache miss, 1 minus H. The key point is that R2, the effective bandwidth that the user gets over the internet is smaller than the effective bandwidth R1 that it gets over the last mile. So that's the user. Now, okay, let's proceed. To get anything out of this model, you need a model for the user. When does he decide to subscribe? And here we assume there's 2 factors that determine the user's decision. It's price and quality of experience. The number of subscribers is given by N, and there are 3 variables that will determine what N is. P is the price, beta is this boost in bandwidth over the last mile, and S is the size of the cache, which determines the hit probability. And there's 2 terms, and the expression we use is a product of 2 functions. D of P gives the demand dependence on price, and we'll assume that D of P is a constant price elasticity of demand model. Constant price elasticity of demand, and that's A divided by P raised to the power of epsilon. Well, that's just a PowerPoint to Apple conflict. P raised to the power of epsilon. And epsilon is that constant elasticity. Whereas the quality of experience is given by Q, and it's a log. It's a transformation of the effective mean effective bandwidth, and log is the function that determines that. Okay, so that's the user model. It tells you how many, the 3 variables that are to be determined that the model should give us, unknown initially, is the subscription fee, P, beta, and S, the size of the cache. And of course, there are, for this model, there are costs. Costs for cache interconnections, costs for the bandwidth, right? So those are part of the model. They are exogenous. Right? So the outline of the model analysis is as follows. The top half shows you social welfare maximization. Now, social welfare is really, maximization is most unrealistic, but it's a very, very useful benchmark for any policy making, right? It's what you use to compare with profit maximization, which is the bottom half. And on the vertical split is non-net neutrality, where beta can be positive, and on the right, net neutrality, where necessarily beta is 0. Right? And if you look at social welfare maximization, there's first best pricing and second best pricing. I'll have a little bit to say about that, but that's basic economics. It's I'll say more. When we get to profit maximization, there's an important distinction. Non-integrated operations, integrated operations. Integrated operations is also not realistic. It's where the content provider and the ISP get together to maximize their combined profit. Right? It's obviously not realistic, but it's, again, for benchmark purposes, very useful because it goes closest to social welfare maximization, where, after all, a social planner overrides the content provider and ISP's interest to decide on social welfare. Similarly, integrated operations is probably the most comparable thing. Non-integrated operations, you need a model, and I think the model that we'll use is something called the Stackelberg game, which is to follow in a moment. So first, the social welfare maximization. I'm not going to spend any time here because it's very basic stuff. Social welfare is really the sum of producer surplus and consumer surplus. If you look at the producer surplus, which is just profit, there's marginal costs, fixed costs, and some revenue coming in, and consumer surplus is the area under the inverse demand function. Now, the first best pricing is just unconstrained social welfare maximization. But what happens then, as you might recall from economics background, is that the fixed cost is just lost to the producer. You know, he just, and that would put the producer out of business. So the second best pricing constrains the maximization to at least let the producer remain in business. So the profit is non-negative. Right? A word about the Stackelberg leader-follower game, which is our model for profit maximization. When the closest, the most realistic model that we have here is the Stackelberg leader-follower game. It's the base model for non-integrated operations. The ISP is the leader and the price setter. The content provider is the follower and price taker, reflecting simply the greater bargaining power that the ISP has. The ISP sets the unit prices for cache interconnection and the extra bandwidth, right? It sets the prices. The content provider reacts to that by maximizing its profit for the given prices, unit prices. And out of that work will come the number of subscribers. Now, that's not the end of the story, because the ISP now optimizes its profit, aware of the policy of the content provider, to determine what those unit prices are that it'll broadcast to the content provider. So it's that final. Now this is the stage where it obviously can't set too high prices, because because it knows that it'll have a reaction in the number of subscribers and how much the content provider will buy. So this is the whole story about the Stackelberg leader-follower game. Now I'm going to show you some numerical results that come out of this model. So just to review things, there are three variables that are up for grabs: the subscription fee, beta, and the size of the cache. These models should give us the answer to those. The rest are exogenous parameters. You know, there's nothing. These are estimates and nothing more than estimates. I won't claim anything more than that. And similarly for the cost. The only thing worth noting is right at the bottom that this price elasticity of demand, an exogenous variable, is just going to be a parameter. All the results are going to be parameterized by that, because we don't really know the answer to that. And moreover, it changes with time. You know, if you like, I'll tell you what my experience from the internet boom about what that is. But that's a parameter. So I won't have time. Oh boy, these results are. This really did get mangled. I won't have time to look at these results in great detail, even if they're perfectly visible, but it'll be worth looking at the landscape so you know what's going on here. That first row, so the vertical, on the left you have net neutrality, and the right triple N. So beta is necessarily 0, as you can see from the third row on the left side of the screen. And the first row is just the price elasticity, and that ranges from 1.15 to 1.8. That's a reasonable range, I think. Just a couple of things to note over here. If you look at the prices for the net neutrality, and then you compare it with the prices with non-net neutrality, you see that there's almost a 2 orders of magnitude higher price for non-neutrality, at least at a low elasticity, that first column. But if you go down inelastic customers, but if you go to elastic customers, then the prices get more equalized, not that much difference. Beta is necessarily 0 on the left, as I said, and the cash hit probability is uniformly high. The quality of experience is on it. I'll review some of this in a summary later on, but here's a graph that shows the horizontal axis is elasticity, going from 1.15 to 1.8. The blue curve is the price under triple N, non-net neutrality, where beta can be positive. And the orange one is the price for net neutrality. So you can see that very sharp, very high prices are there. The quality of experience under non-net neutrality is very high relative to quality of experience. Now remember, this is on a log scale, this is a quality of experience is given by that function Q, which has a log in front of it. So this is on like a Richter scale, right? So these are very substantial differences that you're seeing. And the quality of experience under non-neutrality is much higher at inelastic customer behavior. Finally, the social welfare increase is as much as 150% higher in non-neutrality than net neutrality, at least at the low end. And at the higher end, it's more like 20%. Now I'm going to switch and talk a little bit about profit maximization. Again, the landscape is very similar, these graphs. This thing is the first row is elasticity, then price, beta, age, non-neutrality on the left, net neutrality on the left, non-neutrality on the right. But I think it's this figure that might be, this set of numbers may be a little more interesting. It's comparing social behavior, social welfare maximization on the left with profit maximization on the right. The qualifiers are second best price for social welfare and integrated operations. And again, just a couple of things to note, that if you look at price, the second row across, it's like almost an order of magnitude higher price for profit maximization at low elasticities, and comparable, just a factor of 100% at the low elasticity. And higher bandwidth, and there's something interesting going on over here. Under profit maximization, the cash hit probability has declined from something in the 0.9 to 0.76. So much lower cash investments, and cash is smaller under profit maximization. So let me try to put in words some of these things, and just there's only 2 or 3 things to note. The first thing, so this slide is about social welfare maximization. The first thing to note, and very quickly, is that there's no significant difference between first and second best pricing. Remember, the difference is second best pricing takes the fixed cost into account, first best pricing doesn't. It's not, the way to explain this result is that caches are not expensive, so so the prices are not that different in second best pricing, and hence no significant difference. However, if you go to non-net neutrality, still social welfare maximization, you see 2 scenarios. For low elastic, inelastic customer behavior, you have very high beta,
Excuse me,
high quality of experience.
Wrap up, please.
Oh yes, high quality of experience, and whereas for high elasticity, just the opposite is true. So the social planner has this trade-off, and he chooses for high quality of experience and high prices, few subscribers for low elasticity, and the opposite is high. Now, when you compare profit with social welfare maximization, prices are much higher, extra bandwidth is higher, the cache is significantly smaller, and the quality of experience is about the same. So something interesting is happening here which we hadn't seen before, that cache and bandwidth are being used as substitutes. That in profit maximization, you're using smaller caches and trading that off for extra bandwidth. Okay, so there's one last thing that I want to mention, and this is kind of important. So far, we haven't looked at, there's been no mention of profit maximization in the non-integrated operation setup, when the most realistic case, right? And this chart is about that. And I think a few things really should jump out at it. First of all, so this is profit maximization, the Stackelberg game for the net neutrality case, So beta is necessarily 0, right, for various price elasticities. The prices are much lower, and astonishingly, the hit probability has gone way down into the mud. So caches are not being used. Quality of experience is very low. The number of subscribers is very high. So this is my final slide. So what's going on? When we look at profit maximization in the Stackelberg game, this is non-integrated, for net neutrality, there's a precipitous drop in cache deployment. There are very low prices, low quality of experience, high number of subscriber solutions, and there's very low profit and low social welfare. So the question is why? What happens when you look at the behavior of this model is that the ISP, the Comcast of the world, keep increasing the price for cache interconnection until the content provider decides not to use it. This is truly surprising. So you wonder why again. Look for a more basic reason. More basic reason is that the cache investment under integrated operations and everything in social welfare was comparing first order quantities, marginal profit versus marginal cost. But when we go to the Stackelberg model, the leader follower, price setter, price taker, the rate of change of the content provider's profit is a second derivative effect. It's really very substantially different. I think, so essentially, there's a very unequitable distribution, very low ISP profits, very high content provider profits, and you wonder if there's a smarter allocation process of revenue between the two that would, I think I'm done.
Okay, thank you very much.